Okay. We're gonna do another one. Again, we're gonna start with our toolkit. So let's go ahead and draw our toolkit, just so that we have our full toolkit here. This is my adjacent side, this is my opposite side, this is my hypotenuse. We now have my sine of my angle is going to be my opposite over the hypotenuse. My cosine of my angle is going to be my adjacent over the hypotenuse. And tangent of the angle is going to equal my opposite over adjacent. Okay, we know that for a constant acceleration, we get V final is equal to V initial plus acceleration times time. We get V final squared is equal to V initial squared plus 2 times my acceleration times my change in position. And we get my change in position is equal to my initial times time plus 1/2 my acceleration times time squared. So that right now is our toolkit, and we know that acceleration due to gravity is downward, and it's 9.81 meters per second squared. So we've got our toolkit. All right, so let's look at a different problem. So I'm gonna start from a stop sign. So we're starting from a stop sign. And we've got our little car here that's going. And we're going to go down a distance d. We're going to start with our initial velocity is equal to 0 if I'm starting at a stop sign. And now what we're going to do is we're going to accelerate at 2.5 meters per second squared. And the time that it takes us to get to this spot is 45 seconds. We want to know the distance. Okay, we want to know the distance. So we've got to figure out what we know and what we don't know. So let's look at our equations again. I don't know my final velocity, so that's not really going to help me. I don't know my final velocity, so that's really not going to help me. But I do know my time, my initial velocity, and my acceleration. Okay, that's going to give me my change in position. So I can actually use this information to get there. So there's my change in position is equal to my initial velocity times time plus 1/2 my acceleration times time squared. We're starting with a 0 initial velocity. So I have that. We know what my acceleration is. My acceleration is 2.5 meters per second squared. My time is 45 seconds. And that's squared. So my second squared and second squareds are going to cancel. I'm going to be left with meters. And I'm going to have the right equation. So I can do that. So I'm going to do my 45 squared times my 2.5. I'm going to divide by 2. And since I made up numbers, I've got what's going to be an unreasonable number, but that's all right. This would be a rocket car. Well, maybe that isn't an unreasonable number because we're dealing with a meter. I'm not dealing with velocity. We'll find out if I've got a rocket car here. But we'll have traveled to 2,531 meters. That's our distance or our change in position. We can actually calculate the final velocity now. My final velocity is equal to my initial velocity plus my acceleration times time. My initial velocity was 0. My acceleration was 2.5 meters per second squared. And my time was 45 seconds. So the final velocity is actually 112.5 meters per second. And again, those may not be reasonable because I made up numbers. I didn't actually look at actual numbers. So that's another type of problem that one might have in one dimension. So let's do another one. This time, we've got a person. And our person has an initial velocity of 1.2 meters per second. And we're going to run a distance here. And we're going to travel at a constant velocity. Okay, and we're going to run a distance. I've got a dog with an initial velocity of 0 meters per second. Is going to travel the same distance but it's going to start at time is equal to 5 seconds. We want to know the acceleration of the dog. Because the dog's got to catch up to the person. So this dog, this person is going to run time for the distance is going to equal time. This person's time, or the dog's time is going to be time plus 5 seconds. Distance D's are the same. All right, distance D's are the same. And travel at a constant velocity means that acceleration is equal to 0. So what I have here is I have 2 equations, 2 unknowns. Okay, I have 2 equations, 2 unknowns. Actually, I've got some things that are in here. So this one is the distance is going to equal my initial velocity times time plus 1/2 my acceleration times time squared. And this is for the person. And this is going to end up equaling 0 because I'm at no acceleration. For the dog, right? The dog, I have a distance D is equal to initial velocity times time, which is time plus 5 seconds, plus 1/2 my acceleration, and I have time plus 5 seconds squared. This is equal to 0 because my initial velocity was equal to 0. So now I have my initial velocity times time, and this is at the person, is equal to 1/2 my acceleration time plus 5 seconds squared. We're going to want to solve for acceleration. So I'm going to end up with my initial velocity times time times 2 divided by time plus 5 squared is going to equal my acceleration. And right now, I don't have enough information to actually solve for this. Unless I know the time that it took the person to travel the distance. But I can calculate it for the dog, so I wanted to kind of show you that sometimes we end up not having enough information, but at least we can get a relationship. If you have something like this on an exam, which is one of the reasons why I did it this way. If you have us on an exam here, then what you'll have is that this is how you would leave your answer, and that would be totally correct. Okay, that would be totally correct. But this is gonna depend on exact distance or those informations to get there, but once I have time, I can solve for distance. So that's just another way to approach a problem.